Hey guys, welcome to our Math 112, Section 6.6 Inverse Trig Functions lecture. So before we get started into this lecture, I want to kind of refresh a little bit about inverse functions, right? So in general, if you remember back from college algebra or Math 111, we had kind of a really basic kind of idea that f inverse of x, right? This is the function that essentially undoes the function f. And so this is our notation that we use. This was f inverse of x. And so this is a similar notation. This exponent of -1 on the function name itself is what we're going to be using. A couple of really nice facts or tools with inverses is that we have that f of f inverse of x is equal to x, and f inverse of f of x is equal to x, right? So when we compose these functions together, a function with its inverse, it always will give us back the original input we use. Now, on to our lecture. So every function has an inverse. The problem is those inverses are not always functions. And so in order for a function to have an inverse function, it must possess the one-to-one property. Right? Sometimes we'll just say 1-to-1, something like that. And that is what we're going to be kind of using as our guide. And so what that looks like graphically is, so for something to be a function, for a graph to be a function, we know it passes the vertical line test. For it to have an inverse function means that it must pass the horizontal line test. Oops. Horizontal line test. And what that simply means is that if we look at the graph of any function, okay, for it to be a function means that it must pass the vertical line test, right? Means that any vertical line drawn through that function can only pass through that function one time. If it passes through that function more than one time, it's not a function. The horizontal line test is the same thing, but horizontally. Okay, if we draw horizontal lines, if it ever passes through our graph or our function more than once, it's not one-to-one, which means it does not have an inverse function. And what that simply comes down to is the idea of a function being one-to-one, meaning that for every input, there's exactly one output, which is the definition of a function. And for every output, there's exactly one input. Because inverse functions, as we know, take the outputs of the original and get us back to the input. So let me erase this real quick. Now, if we think about our sine and cosine functions, right? Sine and a cosine function. Obviously, these do not pass a horizontal line test. And so what we can do to be able to work with inverse functions is we can restrict our domain and range down so that they are one-to-one functions on this restricted domain. And if we look at the sine function first, so what we're looking for is kind of the first period where it goes from its minimum to its maximum, where it has all of the min and max values from -1 to 1, 1 to -1, doesn't matter which order. And there's no horizontal line test failures. And if we look at our graph of the sine function, we can see that happens right from here to here. Okay, and that is at -pi/2 up to pi/2. And our range on that region is -1 to 1. Okay, and we can kind of, if we want to get a nice little more specific graph, right? -pi/2, pi/2, -1, 1. It kind of looks something like this. Okay. And so that clearly we can see is a one-to-one function. Therefore, that sine function on the domain of -pi/2 to pi/2 has an inverse function. Okay. So what that means is we can then define the inverse function. So in this case, we can say two different ways. We can say sine to the -1, and that's using that same notation inverse as we've used for f. Or we can also say arc sine. So anytime you see arc and then a trig function, that is simply a trig way of referring to the inverse. And we know the domain and range of functions flip when we're talking about their inverses. So we know clearly the domain and range of the arc sine is -1 to 1, and its range is -π/2 to π/2. Okay. Now, for those of you that forgot this or maybe never kind of saw this idea, to figure out the graph of an inverse function, we can think about flipping the graph across this line y equals x. And so if we do that here, so -1, 1, π/2, -π/2. So how this function here, we can see it kind of swoops down like that and then swoops up. It's going to do the opposite of that. And so it's going to swoop up and then swoop down. So it kind of has this little bit of a flipped effect. So that's what the graph of the inverse sine function looks like. I'm not going to ask you to graph the inverse sine function. I just wanted you guys to see it and kind of be able to understand that. The biggest takeaway here is these domain and range restrictions. So the range restriction for sine isn't it. That's just the range of the sine function. But the domain restriction is a really important thing here. Okay. This domain restriction is what tells us, or what gives us a 1-to-1 sine function. And so what this means is that any angle that we do inverse, or any value that we do inverse sine on, will always give us back an angle in this region. And so we need to make sure that we're aware of that when we're using our inverse sine functions. So let's do a couple of examples really quick. So let's do inverse sine of -1/2. If we look at our unit circle, where is sine -1/2? Well, remember, we're only considering this part of the unit circle, right? Because we're looking at -π/2, so that would be the angle from there to there. And then up here is the angle of π/2, okay? So our sine value is the y value of our coordinate points, if we think about that. So that means this is definitely going to be a negative angle, okay? And what we end up with is that this is the angle -π/6. Okay. Same idea applies to this inverse sine of √2/2. We look for where our sine value or y value is √2/2, and we see that that angle is the angle π/4. Okay. And so anytime I'm giving you these inverse sine functions with these exact values, I'm expecting you guys to utilize the unit circle to help you out. If you memorize it, that's awesome. If you figure these out differently, that's okay too. However, if you do this in your calculator, you would want to make sure that you're in the right mode, right? Keep it in radians mode, basically, from here on out. Anytime we need to switch into degree mode, we'll make that very clear. But if you just do inverse sine, so if you look at your calculator, you've got your sine, cosine, and tangent buttons. And at least on the TI model, right above that, and whatever your second color is, you're going to see sine -1, cosine -1, tangent -1. So you're going to hit second sine, and then let's just do -1/2. So -1/2, enter, and we get -0.52359877756. The problem with that is that's not an exact value, and you need to be giving exact values here. So if you use your calculator for these, it's not really going to help you very much. But let's just try in another line. Let's just do -π divided by 6. We see we get the exact same decimal value. And so we can see that is what the correct answer is. So that's one way you can kind of check your work if you're unsure of yourself using the unit circle. But we want to use this unit circle so that we get answers like -π/6 and not saying that inverse sine of -1/2 is approximately -0.5. Okay. So, if we think of our sine function being anything with angles between negative pi over 2 and pi over 2, our composing the two functions works perfectly and is no problem. So since we're looking at part C here, we're finding the exact values of these things. Since that angle, pi over 6, is within the negative pi over 2 to pi over 2 range, this just undoes itself and it just becomes very simply pi over 6. And this is since negative pi over 2 is less than or equal to pi over 6, less than or equal to pi over 2. Okay. The same thing applies for negative pi over 4, right? And so notice here we have arc sine in one and inverse sine in the other. That's just the same exact thing. So, but again, this is just negative pi over 4, right? Since negative pi over 2 is less than or equal to negative pi over 4 is less than or equal to pi over 2. Now, you don't have to write this whole since thing. I'm just doing that to kind of give us that kind of extra input into this situation. Now, what about here? Inverse sine of 11 pi over 6. The problem is 11 pi over 6 is not between negative pi over 2 and pi over 2. So what we have to do here is we have to figure out what angle between negative pi over 2 and pi over 2 has an equivalent sine value. And that is a very simple problem if you have your unit circle. It can be a very challenging problem if you don't. So what I'm going to do is I'm going to jump out of here and jump into our unit circle. So we're looking at 11 pi over 6. Okay. So to our unit circle, here we go. So 11 pi over 6 we can see is right here. And I can see, oh, that's the same as negative pi over 6. Okay, right? Because we can see that that's just simply one angle down, which is the same as one angle up, just a negative angle. And so let's get this lined up here. And so when we're looking at this inverse sine of 11 pi over 6, we want to rewrite this. Oops. As inverse sine of negative pi over 6. And now, since negative pi over 6 is between negative pi over 2 and pi over 2, this just simply cancels the sine and inverse sine, and we get negative pi over 6. And so this is the most challenging part with these inverse functions, is finding that equivalent piece within that area of the unit circle. Now, I want to jump back real quick to our unit circle. Okay. Notice, what if we had something like, say, 3 pi over 4? Okay, so we're looking at the angle 3 pi over 4. So that's this one here. How do we deal with that, right? I mean, 11 pi over 6 was easy because that was exactly the same as the negative pi over 6. So what we have to do here is we have to figure out what angle has the same sine value as this angle, but is between negative pi over 2 and pi over 2. Since sine is the y value in our unit circle, okay, we're looking at which angle has the same y value, here. And so when we look over to this region, okay, we can see that this is the only one with the same y value. So then that would give us pi over 4. Oh my gosh. Come on. There we go. So that would give us pi over 4. So this is the most challenging part to inverse trig functions. Is figuring out the angle that kind of corresponds correctly. And so it really requires remembering that sine is y, cosine is x, and kind of remembering that whole situation. This is something that is really useful to have this unit circle out because it just gives you a nice visual of this, but is not a necessary thing if you remember it otherwise. So that is inverse sine. Now, if we think about cosine, right, the graph of cosine, okay, it looks like, see, it starts up at 1, goes down and back up. And we can see that if we start here at 0 and then go out here to pi, we get a complete from the highest point to the lowest point, and it is 1 to 1. And so to make cosine a 1 to 1 function, we restrict its domain 0 to pi. Oops. And again, its range just is negative 1 to 1. Okay. And the graph of that negative 1 pi very simply looks like this. Okay. Now, exactly similar to the sine function, when we're looking at the inverse cosine, our domain and range flip. So we get the domain is negative 1 to 1. Our range is going to be from 0 to pi. Now our graph flips a little differently. That was a terrible axis. Negative 1 to 1, 0 to pi. And so if we look back at our original cosine function on this interval, at negative 1, we have the output of pi. So negative 1, we're up at pi. And when we have an output of 1, we're at 0. So that means we're coming back to here. And so this actually comes and looks kind of like this. Okay. Again, I'm not going to ask you to graph these. This isn't something that you need to know how to do, but it is something that is useful in understanding kind of how these relationships form. Okay. So let's evaluate some arc cosines or some inverse cosine functions. So again, we're looking at the range from 0, or sorry, we're looking at the angles from 0 to pi instead of negative pi over 2 to pi over 2. So this is another kind of tricky piece with these inverse functions is you have to remember or have written down in a nice, clear, easy place the range and domains for these cosine and sine functions so that they're 1 to 1 because they're all a little different. And so we need to make sure that we're able to remember what those are and work with those. So here we're looking at arc cosine of 0. So we're looking at when is the cosine function 0? Well, if we think about our unit circle, so with the sine function, we were just looking at kind of the right half. With cosine, we're actually looking at the top half. Okay. Now, when cosine is 0, cosine is our x value, so that would be at this point here. And so that means that this is pi over 2. That was terrible. I don't like it. Pi over 2. Inverse cosine of negative root 3 over 2. Again, we want to look to our unit circle. We want to identify where we have an x value of negative root 3 over 2. And we get that that is at 5 pi over 6. That's this angle right here. 5 pi over 6. And so that means inverse cosine of negative root 3 over 2 is 5 pi over 6. Okay. Now we're doing the composition of inverse functions and cosine functions. And so we have the inverse cosine or cosine inverse of cosine of 2 pi over 3. Because 2 pi over 3 is between 0 and pi, this is just 2 pi over 3. okay? But 7 pi over 6 is not between 0 and pi. 7 pi over 6, if we think about our graph, do this in red, is this one right here, okay? And so this is going to have the same x value of 5 pi over 6. So while I'm still in red, that is 7 pi over 6. And cosine of 7 pi over 6 is equal to cosine of 5 pi over 6. And we can verify that by looking back to our unit circle, looking at these two angles, seeing they both have the same x value on their terminal point. And so this tells me that then this is equal to inverse cosine of 5 pi over 6. So that means this is equal to 5 pi over 6. Now this in-between step here, you do not have to write. That's not something that I expect you to do every time. That is simply something that I am writing to help us in this learning process. So make sure you guys are kind of aware of that. Now, tangent. Again, tangent is that weird guy, right? The graph of tangent looks like this, with an asymptote here and an asymptote here. And those asymptotes are at negative pi over 2 and at pi over 2. This is 1 to 1. Now this would go through the origin minus my terrible drawing. And so what this means is the domain for tangent to be a 1-to-1 function is similar to sine in that it's negative pi over 2 to pi over 2. But the difference is at negative pi over 2 and at pi over 2, we get these vertical asymptotes, so we cannot include them in the domain. So it means our domain for tangent to be 1-to-1 is negative pi over 2 to pi over 2, not including our endpoints. And if we look at the values here, our range is actually negative infinity to infinity. Okay. Just as you see in that graph there. Our function goes like this. Now for the inverse, we've kind of gotten an understanding, hopefully, or refreshed that understanding that the domain and range flip from a function to its inverse. That means the domain of the inverse of tangent is negative infinity to infinity, while its range is negative pi over 2 to pi over 2. And what's that look like graphically? Well, graphically, we would have two horizontal asymptotes, okay, at negative pi over 2 and at pi over 2. And our function would look much like this. Okay? So, what can I do with this? Well, we can do the exact same things that we've been doing with sine and cosine. And so we want to find these exact values. Tangent, inverse tangent of square root of 3 is equal to theta. So what does theta equal? I don't know why I have theta all of a sudden in here on these ones. So theta, so we're looking for the first time between negative pi over 2 and pi over 2 that tangent is equal to root 3. Now it's a positive root 3, so we know it's going to be a positive angle. And so what we get here is we get, I'm annoyed with these zooming in and out, the angle pi over 3. Now, if you remember back to the unit circle lesson, when I did that, right, we had our unit circle and then I wrote those three ratios down. Those are the three ratios of either root 3 over 2 over 1/2 over root 3 over 2, and then the root 2 over 2 over root 2 over 2. Those are the three tangent values we can get for those three angles, pi over 3, pi over 6, and pi over 4. And so every kind of tangent value is going to be either one of those, or it's going to be a 1 over 0 or 0 over 1. And so using that, we can kind of quickly identify these. If it's something that would be benefit to you, if that's kind of a struggle for you is figuring that out, on your unit circle, it's definitely okay if you were to go and say at pi over 6, write out what the tangent of that is. And same thing at pi over 4, same thing at pi over 6, or pi over 3. Write those tangent values out so you can quickly look at the angle, see what the tangent is, and jump to it pretty quickly. Here, when is the inverse tangent? What's the inverse tangent of -1? So the only times tangent between negative pi over 2 and pi over 2 is a 1 or -1 is at pi over 4 or negative pi over 4, because those have the terminal points of root 2 over 2, comma root 2 over 2, or root 2 over 2, comma negative root 2 over 2. And so when we look at that ratio, that's 1, obviously. Now, since we're looking for it to be -1, means one of those two has to be negative. So that means we are looking at the negative angle, negative pi over 4. Now, that's not the negative angle because it's not that necessarily negative values in our inputs mean negative angles, right? We can see that if we go back up here to tangent, right? Negative root 3 over 2 did not give us a negative angle. But with sine and cosine, or sorry, sine and tangent, it is that case because of the fact that we're using negative pi over 2 to pi over 2. So, part C, inverse tangent of negative pi over 3. Well, negative pi over 3 is between negative pi over 2 and pi over 2. Therefore, this just equals negative pi over 3, right? We could add in that since negative pi over 2 is less than negative pi over 3 is less than pi over 2. Notice here I don't say less than or equal to, right? But with both cosine and sine, I said less than or equal to, and that's because cosine and sine include those endpoints, but tangent doesn't. Okay, so if we have something like inverse tangent of pi over 2, that's undefined because tangent of pi over 2 is undefined. Therefore, inverse tangent of that must be undefined as well. So we have to make sure we're careful with that, right? Now, if we look at the unit circle, okay, 7 pi over 4 is this angle here. So what angle is coterminal with that has, so let me rephrase, let me start it. Since this angle is between negative pi over 2 and pi over 2 as far as graphically, we can just simply find the coterminal angle to that. And that coterminal angle is negative pi over 4. Now, if this were to be somewhere else, okay, let's say our whole unit circle, let's say we're looking at this angle here. Is this tangent value positive or negative? Well, remember, tangent is y over x. In the third quadrant, both our x and y values are negative. So this tangent value would be positive, which means what we would be looking for is this angle here. Okay. And so we need to kind of be aware of that and how that's coming around and how we're using these angles and how we're finding these similar angles within our range. And I can't emphasize this enough. That is definitely one of the trickiest and most challenging parts of this, keeping all of that straight. And it just really relies on having really good notes with you. One thing I definitely recommend for this is to have a piece of paper written with notes written on it somewhere that give you kind of quick hits. Imagine if you would like create a 305 card for the test, okay? What you would want to have on that. So things like inverse sine is bracket negative pi over 2, comma pi over 2 bracket, right? So kind of understanding that that's the angles you're looking at, okay? So since 7 pi over 4 has the same tangent value of negative pi over 4, we can rewrite this. We can rewrite this. Let's stick with arctan of tan of negative pi over 4, which is just negative pi over 4. Okay. So that's kind of how we can deal with some of these basic problems. Let's do things a little more complicated. Okay. So if we know that theta is equal to the inverse sine of 20x, we need to find tangent of theta. Okay. This is a problem that's going to have quite a few steps in it, but we're going to start out as simply as we can. Okay. So let's start out first with theta equals inverse sine of 20x. Now, what do I do here? Well, sorry. Take the sine of both sides. So we get sine of theta equals sine of inverse sine of 20x. And what happens? Well, our sine and our inverse sine cancel each other out. And what we end up with is that the sine of theta is equal to 20x. Okay. So let's imagine a triangle or an angle, theta in standard position, that satisfies that. So this is our theta. So sine is opposite over hypotenuse. So opposite is 20x, and our hypotenuse is 1. Try to make that a little straighter. So how can I find out this other side? Well, we can find it out very simply by using the Pythagorean theorem. So what that gives me is that, let's call this side A. We get that a squared plus 20x squared equals 1 squared. So what we end up with is that a is equal to the square root of 1 minus 400x squared. Okay, so perfect. We know what a equals. So that equals the square root of 1 minus 400x squared. Now what? Well, tangent is just opposite over hypotenuse. Or sorry, opposite over adjacent. Tangent is opposite over adjacent. So tan of theta is opposite over adjacent. Now, quite honestly, I would be perfectly happy with you leaving it like this. But we can also rationalize this if you would like, if that would make you feel a little better, right? And just say that that is 20x times the square root of 1 minus 400x squared. Oh, what in the world did that just do? All over 1 minus 400x squared. Now, a couple of questions that I'm sure you guys are having. One of the biggest ones right now is how can we say that sine of sine inverse of 20x is 20x, right? We talked about up there, like, well, the angle has to be in those ranges, right? The reason we can do that is because sine of sine inverse of 20x. So let's look at this. So 20x is a number, right? And for this to work, we have to have that 20x is between -1 and 1. Okay, and that's kind of an assumption that I would say is safe to make at this point. Basically, anytime I give you something like this, it's safe to assume that whatever that x value is has to fit within the realm of possibility. If 20x was outside of -1 to 1, then we would just simply say that, oh, this is undefined, therefore theta is an undefined angle, doesn't exist, and therefore tangent can exist. So we're going to assume that it exists. And so what we get back from here is we get some angle, we'll call it alpha, okay? We get some angle alpha, And we know that because it came out of this, we know, that negative pi over 2 is less than or equal to alpha, which is less than or equal to pi over 2. And it doesn't matter because that goes into sine and whatever that angle is. So then we end up with sine of alpha. And I know that must equal 20x. The reason I know that must equal 20x is because the inverse sine of 20x was alpha. Okay. It doesn't matter if, you want to say, well, this other angle that's outside of negative pi over 2 to pi over 2 will also give me 20x as its sine value. That doesn't matter because when we did inverse sine, it gave us an angle that was inside there that has the characteristic that its sine is 20x. So when we're composing sine with sine inverse, we don't have to worry about these angle issues. It just automatically cancels because inverse sine will automatically give us back an angle within this range. The only time we had to be concerned with whether or not that value was within the range was if we were doing the inverse of the actual, right? So if we did inverse sine of sine, we'd have to worry about that. But because we're doing sine of sine inverse, we don't have to worry. It's going to give us this same output value. Okay. To do another example, we'll do another example with some exact values. So if I want to do say sine of sine inverse of 1/2, okay. Well, what I have to do is I figure out, okay, I'm looking at inverse sine of 1/2. Right? Because we do this piece by piece, following order of operations. So we start with the innermost piece, which is 1/2. That's as simplified as it goes. We move out one layer and we get inverse sine of 1/2. So we need to evaluate inverse sine of 1/2. Well, inverse sine of 1/2 is going to give us what? Okay. Inverse sine of 1/2 is going to give us pi over 6. Okay. And the reason why is if we look at our unit circle, right? I'll go back and we'll show it on here. Okay. So I'm looking for an angle between negative pi over 2 to pi over 2 such that its y value is 1/2, and we see, hey, that's pi over 6. Okay. So scroll down. So I get inverse sine of 1/2 is pi over 6. Well, what's sine of pi over 6? That's just 1/2. Okay. Now, are there other angles that will give me a sine that is equal to 1/2? Absolutely. But that's not what we're dealing with here, right? And so there's no point in this where I had to kind of think, oh, what, is this value between these things? It just automatically kind of worked. And so that's why we're able to automatically cancel the sine and inverse sine in this order. So if you have sine of sine inverse, they just automatically undo, no worries. If you have inverse sine of sine, they don't necessarily undo because that sine function is not always 1-to-1. So we have to be careful. Okay. So that's that example. Again, I would be fine if you stopped at tangent of theta equals 20x over square root of 1 minus 400x squared. But if you want to rationalize it, that's perfectly fine as well. So here we're given some information. We are told that A is equal to 1, C is equal to 7. Okay. So we know that A equals 1, C equals 7. We need to figure out what alpha and beta are in degrees. Notice, in degrees. The first step, if we want to, is to find the side B. We use Pythagorean theorem to do that. And it gives us the square root of 48. But I'm not going to use that at all, right? We don't need to. Because if I'm looking at angle beta, okay, I have its adjacent side and I have the hypotenuse, which means I know that cosine of beta is 1 over 7. How do I get rid of this? How do I get rid of this cosine so that I can get just beta? Well, you take the inverse cosine of both sides. These cancel out. Again, right? We're working with this. It's not the same as what we had here, but we are working with this. And if you kind of want to draw this, you can see, hey, that's in the first quadrant. We're good with both of these angles. They're both acute angles, so they both fall within the 0 to pi over 2 range, which means they are both fine for either cosine or sine. Okay, and so we can just whip this through and get beta equals inverse cosine of 1/7. Now, how do I do this, right? Because we need to get the degrees. Well, we grab our lovely little calculator. We make sure we change the mode into degree mode, because if we keep it in radian mode and we do this, we're going to get a bad answer. And we want to take the inverse cosine of 1/7. And when I do that, I get that beta is equal to, instead of equals, I'm going to say is approximately equal to 81.787. Okay. Now, we could use this and the fact this is a 90-degree triangle to simply, this is a right triangle to do. So 81.787 plus 90 gives us 171.787. Do 180 minus that, and we get that alpha must be 8.213. Okay, so that's just using the fact that the three angles in a triangle add up to 180. But let's just practice our trig inverse functions for now. So I know that the sine of alpha is 1 over 7. Since with angle alpha, I know the opposite and the hypotenuse. Do the exact same thing as we did on the last problem. So we take the inverse sine of both sides. Again, this cancels because alpha is acute. We know it works. So we get that alpha is equal to inverse sine 1/7. So alpha is approximately, if you do this on your calculator, we get 8.213, which is exactly the same thing we got when we just use our geometry ideas to find that. Okay, so we're almost done. We have 2 more problems left I want to go through, and I will get you guys out of here, get you guys done. So solve the equation 3 sine of theta equals 4/9, where theta is in degrees, is acute. Okay, so that's a big key right there. Theta is acute. So we know it falls between 0 and pi over 2. So we know that sine and inverse sine and all of that stuff cancels out smoothly. So just like any other equation, okay, we deal with this the same way. Now, one thing some people get really messed up with is when we've got sines in here, how do we deal with that? If you wanted to almost, you could replace that sine with like a, let's say x, since our angle is theta. So we almost have 3x equals 4/9. So you would solve for x, and then you would replace back that x is sine of theta. So you get sine of theta equals that, use inverses and go from there. But I'm going to treat you guys as mature mathematicians, and we're going to deal with it as is. So the first thing to do to get rid of this 3 is we need to divide both sides by 3. And in doing such, we end up with sine of theta equals 4/27. Well, this now looks exactly like what we dealt with up there. We just need to take the inverse sine of both sides. And since we know that theta is acute, I know that these are just going to cancel out, leaving me with theta equals inverse sine of 4/27. Again here, this problem tells me that theta is in degrees. So we keep our calculator in degree mode. Inverse sine of 4/27, and we get that is approximately 8.520 degrees. And I didn't do that up here. Let's do that. And degrees. That's it, right? So solving these trig equations are really just like any other thing. We just use these inverse trig functions to get rid of these trig functions, just as we would if we had, say, something like the square root, or if we had something more complicated, but we knew what the inverse function was, say like an exponential, right? If this equation was 3e to the x equals 4/9, we would divide both sides by 3. And then to get rid of e to the x, we would take the natural log of both sides, because natural log and e to the x are inverses. And so we'd end up with x equals the natural log of 4/27, so we can evaluate that. So this is no different than those problems. We just need to use these functions. We have to check to make sure that these equations have angles that are within the range of use. So now I want to write the following as an algebraic expression. What does that mean? Well, what we want to do is we want to think about what inverse tangent of u means. So let's just, for a second, let's say, okay, well, inverse tangent of u, or tan inverse of u equals theta. Okay? So that's, not jumping to any conclusions. That's just saying that the inverse tangent is going to give us an angle. Well, what if I take the tangent of both sides? Okay, so I get oh man, this is so fun. I get tangent of inverse tangent of u equals tangent of theta. Well, tangent of inverse tangent, we don't have to worry about those angles or anything like that, or those values, right? Those just cancel when we take these trig function of its inverse, just everything works out. And so what we get is that u is equal to the tangent of theta. That's a terrible theta. Cool. So what in the world do I do with that? Okay. So I know tangent of theta is equal to u. Okay, so let's give us a triangle real quick. Okay. So if I have a triangle, okay, this is our theta. So tangent is opposite over adjacent. So that means we have u over 1. Okay. So what I'm trying to figure out, right, is I'm trying to find sine of inverse tangent of u. But we said, let inverse tangent of u be theta. So what we're asking here is, this is the same as, what is the sine of theta? Well, to know that, I simply need to know the opposite, which is u, and I need to know the hypotenuse, which we can find by using the Pythagorean theorem. That's just 1 plus u squared. Square root of 1 plus u squared. So sine of theta is u over the square root of 1 plus u squared. Again, I'm okay with you leaving it like this, but if you'd like to further go through and rationalize that denominator, u square root of 1 plus u squared over 1 plus u squared. Now, there's no simplification that happens here. Nothing really drops out or anything like that. It just is now rationalized and, things like it more. And so that's it. So what we're doing here with these inverse functions is really just using them to cancel things out, make things go away. Now, this is maybe the trickiest problem, and I would love if we were in class and we could, engage in some conversation about this. If you have questions, on any of these examples, please write them down and email them to me, or post in the questions forum, and I will get back to you guys on these. But yeah, so that's it. These aren't really that crazy. They're just maybe a little new, and so that makes them kind of challenging. But that's pretty much it. So that's the end of chapter 6 for us. So now we're going to move on to chapter 7 in our next lecture. You guys have a great day, and I will see you guys with 7.1.